So last time we finished talking about double slits, the double slit interference, and we also talked about diffraction gratings, multiple slit interference. So today we're going to just continue this train of thought, and we're going to talk about, please, right, single slit interference. Now you might say, how would a single slit cause interference? It's only one source. And the trick is that the Huygens principle only applies for infinitesimally small wavefront points. But real life slits have, real life slits have have thickness. So it's not an infinitesimally thin diaphragm. So in practice, like in the real world, if we made slits that were infinitesimally thin, so that it was truly just a point particle or a point infinitesimally thin across, like what we modeled, then none of the light would get through, right? You'd be basically blocking all but an infinitesimal amount of light. And so you would end up with no light on the back screen. So because of that, we have to actually take into account what happens if the slits actually have some width. Now, they don't have to be super wide. They can just have a little itty bitty width, but they have to have something. So we need to account for that. So to study this phenomenon, we are going to consider just a single wide opening. And we're going to see if that produces any interference effects. Now, so the picture here is you have a single wide opening, say, of width d, and we're going to shine a laser through it like we usually do. And then the question is, what do we see on the screen on the other end? Now, unsurprisingly, we get a bright spot directly across because the light goes through. So there's going to be light that comes from all sides of the slit. I cannot write, or draw rather. Right, you're going to get light that comes from all parts of the slit, and you're going to get a bright spot there. Now the question is why do we get a bright spot at the center? Now, I mean, it might seem obvious, but we're treating these as individually interfering waves from every single point along that slit, right? So why does it have to be that indeed there is a bright spot at the center? Well, it's because all of the Huygens pairs, or all of the Huygens points, rather, these are the points that emit their own spherical wavefront, they pair up with another point on the opposite side of the midpoint. And so what that amounts to is that the top point pairs up with the bottom point. The one that's a quarter of the way down pairs up with the one that's a quarter of the way up, and so on. And so those will all travel the same distance by symmetry. And so because they travel the same distance, they will constructively interfere. Now, it doesn't have to be the case that each pair constructively interferes with other pairs. But it turns out that for the most part, this does happen, and the math is kind of complicated, so we're not going to go into it. But we can just verify this experimentally, that there is a bright spot at the middle, and it's exactly as you would expect. If there wasn't a bright spot in the middle, that would be very surprising, right? So that tells us that as far as we know, or as far as we can tell, there will be a bright spot, say, here. And maybe it'll spread out a little bit or whatever, like the single slit does, or like the double slit or the multi-slit does, but there will certainly be a bright spot at the middle. Now, the question is that the only bright spot? Now, if this just behaved as you might expect, like for a large opening it would, you would just have a bright spot in the middle and nothing to the sides. But this slit side, or this opening is narrow. This aperture is narrow. It's not infinitesimally narrow, but it's narrow, so there might be interference effects. So we need to ask the question, what happens at increasing theta? Now, the point is theta measures away from the horizontal just as before. So theta measures, if we were interested in this point, theta would be something like this angle here, right? So just like with the double slit, just like with the multi-slit, just like with the diffraction grating, we're measuring position along the screen as an angle off of the horizontal. So eventually, so there will be a bright spot in the middle, and eventually we will reach an angle so that each Huygens point on one side of the center line has a mate on the other side of the center line whose path length is longer, right? Because as we angle up, the ones up top, the Huygens points up top are going to travel less far to get to that point than the Huygens point below. And so eventually we will reach a point where, I'm going to zoom in just to erase some of these. Oops. Oops. I'm actually going to erase all of those lines now that I think about it, just because they're cluttering. So for example, at some angle, it would be the case that if you take a point here and a point here, the bottom point is going to travel half a wavelength further than the top point. There is some angle where that will happen. So let me just draw a zoomed in version. So here's our slit, and here's our screen. So for example, if we take a point here, and let me draw our middle point. If we take a point here and here, so one point at the top and one just below the midline, and we take a point, say, just above the midpoint and just above the bottom, those are the same distance away, right? That distance is basically, I mean, because one's just at the top and the other's just in the middle, that distance is A over 2. Oh, reminder, sorry, that's not labeled A, that's not labeled D, that's labeled A. We use a different variable for single slit width just so we don't confuse them, because we're going to combine them eventually. So the aperture size, this is the size of the opening, that is labeled A. So this distance is roughly, or in this case, it's actually exactly A over 2. And so we want to know, well, we want to know what angle does, say, this distance, the distance that one travels further than the other, is that equal to lambda over 2? And because each Huygens point would pair off with one exactly A over 2 units lower, each point would be paired with one. And if that distance is lambda over 2, then it'll be lambda over 2 for all of them. And so once the path length difference for every pair is lambda over 2, we know that that's when destructive interference occurs. Delta x is lambda over 2. Then delta phi, remember that's the total phase change, is 2 pi lambda over 2 over lambda, which in this case the 2's cancel, the lambdas cancel, and you're left with pi, which implies destructive interference. So long as, so this is all to say, I'll leave it at that. So this is just saying you can pair off an infinite number of points. You pair off the top infinitesimal point with the point at the middle line. Then you move an infinitesimal amount down. You pair off that point with one that's infinitesimally lower than the middle than the first point you paired with. So you just keep going down, and every point ends up being paired with exactly one that's A over 2 away. And then from the same geometry that we did when we were talking about double slits, that the path length difference, or when the path length difference is when the path length difference is lambda over 2, we would get destructive interference. And because they're all destructively interfering with one other point, you get no light from any of them. And so the end result from every point on the slit is no light. Now, the question is where does this dark spot or this dark fringe appear? So this would produce a dark fringe, and there would be a place that's the first dark fringe. So you have a bright spot, and then you have a dark spot somewhere else at some other angle, right? So where? So we've already established that for 2 point sources, like in the double slit case, if their slit separation is D, then the first time that you have, or then the path length difference, the path length difference as a result of their vertical separation is d sine theta if they're separated by d units and they make an angle theta with the horizontal. So that is to say, d sine theta equals delta x. Here, d is A over 2, because that's the distance between the Huygens points that are paired with the other one, or that's the distance between the Huygens point that's paired with one, or that's paired with the one that's halfway down, right? That's the distance for all of the pairs. And so to get destructive interference, the first fringe, not constructive, destructive, we would have that a over 2 sine theta, because in this case d is a over 2, should be equal to lambda over 2. We want the path length difference to be lambda over 2. That's where we get destructive interference. And so we can just solve this, and we find that the first dark fringe, so this is for single slit interference now, so this will look familiar, but it's not the same formula. The first dark fringe occurs when sine of theta equals plus or minus lambda over a. So I just canceled out the 2's and divided by a. So this is the first dark fringe, and there will be one on either side for positive angle and a negative angle, right? And so this occurs when sine of theta is equal to lambda over a. So you can just find the angle by taking the wavelength and dividing it by the slit width. So the next question is, where do the next dark fringes occur? So we're investigating dark fringes for the same reason we investigated bright fringes first last time. And it turns out that dark fringes are easy in this case to find, bright fringes are not. So, okay, so like I said, we need to figure out where the next dark fringe is. Now, we could maybe just put a 2 here, or, well, no, we wouldn't want to put a 2 there, because if we put a 2 there, then we might think that we get constructive interference. So let's think about it a different way. We need to pair up points that are so that their path length difference is lambda over 2. Now, if we increase the angle, so our first dark fringe maybe occurs here. If we increase the angle, then we can decrease the distance between them and still get the same path length. So instead, let's pair up, say, points that are a third of a, I think that actually might be wrong. No, that's right. Let's pair them up a quarter of the way down. So you might think, well, why not a third? So we can certainly pair them up halfway. So each one is paired with one that's halfway lower. But you might think, okay, well, why not a third? Well, let's try that. So if we pair them up into a third, well, so this one would be paired with this one would be paired with this one, and so on. And then the one that's just above the one we just paired with would be paired with this one. But all of the ones that are in the middle here have already been paired, so there'd be nothing to pair with the ones on the bottom. Instead, we're going to ask that they're paired up a quarter of a distance away, a quarter of a slit width away. So in that case, the picture would look like this. So we have, I'm going to draw a middle line just as a reference, and I'm going to draw another middle line, a quarter line. So the top one would be paired up with one just below the quarter line. Then the next one down would be paired up with the next one down, and so on. So we treat this just as its own single slit, and there will be destructive interference between those angles. And that will be a larger angle because the slit width is effectively smaller. And then we do the same thing here. This one will be paired with this one will be paired with this one, and so on, all the way down. And now every point is paired with exactly one other point, and they form destructive interference. So here, we would want that lambda over 2. Let me write that this distance here is now a over 2. That's the distance between, that's our new single slit width, and then we're just doing that twice. So here, we would have that lambda over 2 should be equal to, well, what's our, sorry, let me back up. So a over 2 is our effectively our new single slit width, but the distance between points, this distance here is a over 4. It's half of that new slit distance. So we would want lambda over 2 to be equal to a over 4. That is our new d, right? Looking back up to the top. That is our new d. It's a over 4 now because that's the distance between the pairs. And then this should be equal or times sine of theta. That's our new, this is our path length difference, d sine theta, and that gives us, and if we want that to be destructively interfering, then we get lambda over 2. And so this implies that our second dark fringe occurs when sine of theta equals 2 lambda, or plus or minus 2 lambda over theta. Sorry, plus or minus 2 lambda over a. So this is our second dark fringe. And you can probably extrapolate. We could break it up into sixths, into eighths, into tenths, into twelfths, and so on. And all you're doing is you're just incrementing that number there. So we can extrapolate, and we find that the dark fringes for this pattern occur when sine of theta is equal to m times lambda over a, where this is for single slit, by the way, where m is, it's all of the negative integers, 0, positive integers, sorry, not 0. 0 is not, we have to skip 0. That's wrong in my notes. By the way, the reason why we skip 0 is because when sine of theta is equal to 0, you get a bright fringe. So that's the exception. So let me actually make this a little better. So -2, minus 1. And then we skip 0, and then we have 1, 2, ... And let me move this over. So we skip 0 because that's actually where the bright spot is. And we know that that's where the bright spot is due to constructive interference. It's just there's dark spots here. Now, what does this indicate? This actually indicates something interesting. It indicates that except for the first 2 dark spots, i.e. the one to the left of the bright spot and the one to the right of the dark spot, the dark spots are equally spaced. They're angularly equally spaced. Meaning, well, yeah, I'll just leave that out. For small angles, at least, they are just equally spaced. For large angles, you have to account for the fact that the sine of theta doesn't equal theta. And on top of that, the central maximum, and so, by the way, if there are dark spots that are spaced out, that means that there's bright spots between them, right? Like, it wouldn't make sense to have dark spots and then more dark spots between them, because we know all of the dark spots now. So there are bright spots between each of the dark spots. So in particular, the central maximum, well, on top of this, the bright spots are also equally spaced if the dark spots are equally spaced. Because there's bright spots between dark spots. Now, a consequence of this, the fact that the bright spots are equally spaced, well, so we know that we have I'm just going to draw a point plot here. We know that we have a bright spot here, and we know that we're going to have a dark spot here and dark spot here. And we know that these dark spots are equally spaced, right? This is a rough picture. So that means that the bright spots, however bright they are, they're going to be equally spaced, except, and they have some particular width, except the central one is much wider, right? Just because if we follow the pattern, then there should be a dark spot in the middle, but there isn't. So the middle is an exception. So the central maximum has twice the width of the other bright spots. And in fact, it's also true that the central maximum has twice the width of what the width would be for the central maximum if this was a double slit setup where instead of A, we had D. So, so now that we know where the dark spots are, I linked to an example that you can work through if you want to. And now we have to get to something horribly, horribly messy. And for that, I apologize. What we're about to see is potentially, or actually not yet. We are going to see something bad, but we're going to see something even worse shortly. But there's going to be a demo in between, so at least you have some relief there. So just like with the double slit case and the multi-slit case, we worked out the intensity as a function of angle, right? We can do the exact same thing here. It's just a lot worse. So I'm actually not going to derive the solution, but the solution is the way it can be derived is found in most textbooks. It's not in the LibreText either, by the way. It's basically a result of adding up an infinite number. Remember when we derived the multi-slit intensity? We added up 4 wave functions that all had distance. Sorry, a path length difference between each of them. It was like by d sine theta. Yeah, like d sine theta. We added up all of those. Here, you would add up an infinite number of waves, each of which are an infinitesimal distance away, and then you basically do an integral. But it's a little bit beyond the scope of this class, so I'm not going to do it. So just like before, the intensity depends on the relative phases of the waves. And because the relative phases of the waves, or the relative phases of the source waves, are depend on angle, the intensity here depends on angle. And that shouldn't be surprising. The intensity, we found that there are bright spots and dark spots at different angles. And so, of course, the intensity varies on angle. So to get that, again, like I said, it's a nasty integration. But the result for the intensity function for a single slit of width A is I of theta equals I naught being the brightness at the central maximum, times sine of alpha divided by alpha squared, where alpha is pi a sine theta divided by lambda. So it's a nasty function. It really is. This I naught is the central maximum intensity. And this function actually has been given a name. When you have sine of something divided by that something itself, it's called the sinc function, S-I-N-C. And it shows up pretty regularly. That's why it has a name. But it's literally just like sinc of x is just sine of x divided by x. That's all. So if you want to find the intensity, first you have to figure out what alpha is. So you find theta, or you plug in theta, a, and lambda. You plug that in, find out what alpha is, and then you plug that in to sine of alpha over alpha, square it, and that will give you the relative intensity. Alternatively, if the angle is small, then alpha is just pi ay divided by lambda L, where y is the distance up the screen, right? Just like it's using the same approximation. If the angle is small, then sine of theta is approximately equal to the tangent of theta, and tangent of theta is y divided by L. So both of these equations will be useful. Obviously, the one that's in the box is technically more correct because you're not making an additional approximation, but they both involve approximations. So depending on the situation, one will be more useful than the other. Now, as you can check, and actually, let's just check the first example. We can check that the location that we determined for the first dark spot does agree with this intensity formula. So for the first dark, or the first dark fringe rather, occurs when sine theta equals lambda over a, right? Plus or minus lambda over a, but we're just going to use lambda over a. This means that a over lambda sine theta is equal to 1. And so we can plug that in to alpha. Alpha is a sine theta over lambda times pi. This implies that for this first dark fringe, alpha is equal to pi. And so that means that I of, well, what's the angle where the first dark fringe is? It'd be the arc sine of lambda over a. This is just equal to I naught times sine of pi divided by pi squared. And sine of pi is just 0. So this is just a good check that our logic above agrees with the formula that you get for the intensity, that if you plug in this, if you plug in the location, the angle of the first dark fringe, you get an intensity of 0 out, which is exactly what you expect from a dark fringe. So let me just plot for you what the intensity sinc function looks like. It looks something like this. So this width here, the width of the bright central maximum, that has a width of 2 lambda over a. And then each subsequent bright spot has a width of lambda over a. So the bright spots are half as wide as the narrow spots. Also note that the dark spots are evenly spaced. Also, this has width lambda over a. By the way, this is measuring theta, and this is measuring I. They're equally spaced in angle. So the dark spots are equally spaced, just as predicted. The central bright spot is significantly brighter than all of the subsequent bright spots. It's about 20 times brighter than the following bright spot. And something else, and this is not just an artifact of me drawing it poorly, but I also did draw it poorly, is that the bright spots aren't evenly spaced. And you can perhaps think of why that happens. That happens because the intensity drops off with distance. So that means that where there might be a bright spot, like, so I drew this poorly, it should actually be to the other side. Oops. Where you might expect there to be a dark spot halfway between where you might expect there to be a bright spot halfway between dark spots, it's actually not there. It's slightly to the left because the intensity also drops off with distance. I mean, it drops off with as 1 over the angle, as we can see here. It drops off as 1 over the sine of the angle. And so where there would be a bright spot halfway between them doesn't have quite as much intensity as something just to its side, because the intensity is also affected by the angle, by the sine of the angle away from it. So your bright spots are shifted a little bit inwards. And in fact, solving this equation for those angles explicitly is just not a thing that you can do. There's no algebraic way of doing that. You have to do it numerically. That is, the zeros of the sinc function the maxima of the sinc function are just not, they're not algebraic numbers. In fact, they're not even, even more, well, you guys don't know about this. So basically, you can't solve for them with algebra. There's just no way to do so. You can only do it numerically. So this tells us what happens if you have a single slit of a finite width. Now we can slap them all together and see what pops out. So what happens if you have 2 finite width slits? Finite width slit, finite width double slit setup. One sec. Sorry, I have company. Right. So here, this would have both effects. This would have the effect from, where is everybody today? Okay, whatever. This would have the effect from, well, each slit is finite, and it would have the effect from the 2 slits interfering with each other. So the end result of this is that you end up combining the effects from both slits. We're assuming that they have the same width, by the way, or from both single and double. So one way to view this, and this is described really well in the Liber text, is if you have a single slit pattern, if you have a plane wave, just like plane waves just moving towards your single slit, then the single slit tells you how that interference pattern will look on the screen. It would look like something like this. So you have a plane wave coming in, and the output on the screen looks like this. Basically, it shrinks down the intensity at some angles, at these zeros, and it leaves the intensity unchanged at other angles. So we can think of the single slit as kind of like an envelope that affects, or that all it does is it just smushes down the intensity at specific places. You could think that the intensity would have been just flat if there was no single slit, but the single slit, what the effect of the single slit is to just push this bit down, push this bit down, push this bit down a little bit less, and so on. And so what we can do is we can imagine, okay, this is what happens if you have a plane wave coming in. What if you have a different thing coming in? What if you have the interference pattern from a double slit? Then what would you get? Well, it would have the same effect. It would push down the intensity pattern at different places by different amounts, and it pushes it down the same way that it pushed it down for the plane wave. It's just the double slit effect, the double slit interference pattern, already has its own pattern built in, and then it's smushed down by the single slit effect. One way to see this is that if the single slit interference pattern, let me actually write this down. So we can look at a specific case. What happens when one formula, whether it's the single slit formula or the double slit formula, when one formula says a dark spot and the other formula says a bright spot? We're talking about multi or single and double slit here. Well, so we can imagine this in two ways. So let's say that according to the double slit formula, the pattern for, or the formula for intensity of a double slit interference pattern, let's say that there would be a bright spot at some angle. Maybe the angle is 5 degrees or something. But if you plugged in the same parameter, the same angle for the single slit diffraction pattern intensity formula, let's say that at that same angle, you would get a dark spot at that place. Well, what would the end result be at that angle after you do this measurement? You would find that there's a dark spot there. And the reason for that is that regardless of what's incoming from this, towards the single slit pattern, the single slit pattern is only going to let certain amounts through. It'll only let light through at places where there is no dark spot. And so regardless of how bright the double slit pattern is at that bright spot, so I'm doing my best to explain it now. So this is an explanation as to why. So let's say that basically view it this way. So you have your double slit and you have your incoming wave. That produces a wavefront that looks like this. And we can treat the single slit as just following the double slit. And so then what we would see on the screen is we would see, well, even if there would be a bright spot from the double slit, say from this part of the wavefront, well, if the single slit would say that there'd be a dark spot there, well, then the dark spot lets no light through, even if there would have been, like, the point is regardless of what's coming in, at the dark spot, there's no light. So that means that the light from the dark, or the lack of light from the dark spot, wins. And the same is true vice versa. So because the distance between the two slits are small. No. So we're actually, like, this is an abstract thing. They're not actually separated. It's just like it's actually, they have finite width A and finite separation D. It's just we can kind of decompose the problem or decompose the situation as to first double slit, then single slit, or vice versa. Probably vice versa is the most reasonable way to view this, but it works both ways. Where is it going with this? Right. So the dark spot wins in this case. If one formula says a bright spot and the other says a dark spot. And the way to see this is that 0 times a maximum intensity is still 0, which implies that we really need to be using multiplication. So saying we can view this as a double slit problem or as two single slit. No, it's saying that we have to view it as both. That if you have a double slit setup where the slits have finite width, then it's a combination of them. And in particular, the way that we combine them is by multiplication, because if you multiply 0 by maximum intensity, you still get 0, and that agrees with the argument that we just made. The natural way to do this is the natural way to combine them. So you may have thought, okay, well, maybe we combine them by adding, maybe we combine them by subtracting or whatever. It turns out that because the dark spots beat the bright spots or win, i.e., if there's a dark spot according to one formula, then there's a dark spot there regardless. That implies that the way that we combine these formulas is by multiplication. So the intensity formula, so I think my computer says the slits didn't already have finite width. No. When we were doing the double slit setup, we assumed that the slits had infinitesimal width. Yeah, so this is if our width isn't infinitesimally small, like in any lab setup. And by the way, this is why I didn't do an actual double slit setup for as a demo, and that's because you can't get a perfect double slit setup because you need infinitesimally thin slits. So the end result is the nastiest formula you will see in this course and in 9C. We get that the intensity as a function of angle sorry, not as a function of y, as a function of angle is equal to I naught. That's the maximum. Where did D end? Oh, sorry. Let me just draw a picture. Let me draw the picture again. So the setup here is we have two slits. Each one is width A, and the distance between these two slits, measured from the middle point, is D. So this is the setup. So the intensity for this setup as a function of angle is the maximum intensity, because these are always relative intensities. So the intensity at the bright maximum spot times the cosine. Well, this first part is just the double slit one, pi d sine theta over 2 or over lambda. And then we multiply that by the intensity for the single slit pattern times sine of alpha divided by alpha squared, where alpha is pi a sine theta over lambda. That is the finite width double slit intensity formula. Yeah, I know it's terrible, but this is a formula that like you can just directly apply in real life, because you can just measure the width of your slits, measure the distance between them, shoot a laser at it, and then this will actually match the result that you get. Like actually real life. This is, I mean, it's not exact because we made some very small approximations, but assuming the wavelength is smaller than the slit separation and then the width, so like the wavelength is 500 nanometers and the slit separation is 50 microns. Why don't we simplify it by plugging in alpha and simplifying? Because it doesn't simplify. You can't like the reason why we separate out alpha is because if we don't separate out alpha, it gets really, really nasty. Like it's just not simplifiable. This is as nice as it gets. Like you can try and see, like it won't get, I mean, like you can move some of these constants out to the other side, but it's not gonna get nicer. So let me draw a picture. So the picture of this single or of this double slit finite width intensity, and this is going to be terrible, but I'll do my best. So there's a bright spot in the middle. Actually, let me draw the envelope. So we can view this as an envelope surrounding a double slit. So this is what it would be if it was single slit, right? It would be like that dotted line. Does a finite width affect the distance between bright and dark spots? Yes, but only a little bit. Assuming that the distance between the slits is greater than the width of the slits themselves, which is kind of necessary, then your bright and dark spots will be significantly closer. Oops. They'll be more narrow, and so you'll like this distance here is the same, or rather this distance is roughly this. Well, no, it is. It is just the same as it would have been for the double slit. So this is the pattern that we end up with. That is what we would get for the double slit finite width setup, which is interesting, and that's actually what we observe. If you were to actually get two slits, that's what we observe. Now, there's one more thing to talk about. This about the single slit setup, or the single slit principle. Sorry, the single slit interference experiment. I can't talk today, and that's Babinet's principle. I think it's Babinet's principle. He's probably French. Might be Babinet's. Who knows? So Babinet's principle is just that the diffraction pattern from an opaque body is identical to that formed by a hole of the same shape, of identical shape and size, aside from, sorry, I'm just copying this explicitly, aside from the overall intensity. Now, there's an upside to this, and that's that we can use it in a demo. So by the way, this is saying like if you have 3 slits, and then like if the picture is that if you have like a sheet of paper, right, and you have 3 slits, and those are the only places through which light can pass, right? Imagine that like you have a piece of paper and you're shining light through these 3 slits. Okay. Ah, shoot. You guys get it though. Well, that would form an identical pattern as if you shined a light at just 3 solid things of the same size and shape. If you shined a laser at this setup and you shined a laser at this setup, you'd get the same type of interference pattern. It's just one might be brighter than the other. This one will be brighter because it lets more light through, but the pattern will be the same. You'll have dark spots at the same place and bright spots at the same place. So this means that we can model a single slit interference pattern just by having, rather than having something opaque with a very narrow slit in between, we can get a single slit interference pattern by just shining our laser at something very, very narrow. Now, we all have something very, very narrow that's accessible and easily used in a demonstration, and that is a single piece of hair. Now, I'm going to stop sharing for just a minute as I show you this demo, and we're going to do it. So here I have a laser. This is a different laser. And don't mind the non-scientific setup. It is a bunch of coasters, and the laser is taped to the coaster. Here, I don't know if you can see this. Between these two, well, actually, you can probably see it just by me pulling. So between these two, is a hair of mine that I've suspended between these 2 fridge magnets. Sorry, this fell over. Notice how one tugs on the other. I don't actually know if you can see it. It might be too small. And what I'm going to do is I'm going to take this laser, shine it at this hair. Can you see this? Maybe. Might be. There you go. Now you can see it. There's a hair there, a single hair. I'm going to shine it at this hair, and this will exactly mimic. It will produce an interference pattern that exactly mimics the interference pattern of a very, very narrow slit, a slit that is as narrow as my hair. Now, human hair, my hair is probably somewhere between 20 and 50 micrometers across, so that's a very narrow slit indeed. So I'm going to turn this on, and I'm going to try to set this up. Getting the alignment right will be rough, so we'll do our best. So here's our, can you see that? Oh, is that way too bright? That might be way too bright. Oh, no, never mind. There it is. Okay, so I'm going to try to set this up. Oh, that's perfect. That's beautiful. Okay, so it's actually, you can even see the beam a little bit. I don't know if you can see this, but maybe you can. Yeah, I don't think you can, but you can see that the laser's hitting the hair. Now I'm going to take you over here. We can actually see. I want to make sure that that you guys are seeing what I think you're seeing. Let's take it closer. Let me block just the middle bit. So if I block just, where'd it go? If I block just the middle bit, hopefully you can see little tiny what is happening? Oh, wow. You can actually really see the beam this way. See, looks pretty cool. But you should be able to see little itty bitty diffraction patterns. So there's the bright spot. And then right here, you should see a spot that's not bright, a dark spot. And this is a lot more impressive in person, I just realized. It doesn't come well across in this camera. But what I can actually, yeah, you can see it a little bit. So what I could actually do is I can measure the distance. I've already measured this distance. It's something like 85 centimeters. I could get out a pair of calipers And now I can just measure this distance. That distance works out to be about 12 centimeters. Distance between the central bright spot and the first dark spot, it's about 12 centimeters. And sorry, 12 millimeters. I can plug it into the formula and I can calculate the width of my hair just by using the single slit intensity formula. I've done that calculation already offhand, and it works out that I'm approximating here, but it works out that my hair is something like 45 to 50 micrometers across, which is just about right for human hair. So this is actually like a perfect demonstration that the intensity formula works exactly. And the reason we had to use a hair is because you need something really thin. Otherwise, your bright spots, or otherwise your spots are very, very, very close. We need something as thin as we can get. Sorry, we need something as thin as we can get, so that the dark spots are as spread out as possible. Right. So let's continue. So that's basically the end of like interference by like having two camera. We're not gonna like that. So we already talked about two slits. We talked about more than two slits. Now we talked about one slit. So that's all of the possibilities. Now we just got to move on. We're still talking about interference, but we're going to talk about different kinds of interference. So the first kind of interference that we're going to talk about is we're going to talk about interference as a result from reflection. So this is also known as thin film reflection. This is a section in the book. I want to say it's section 3.5. Yeah, I think it's section 3.5. And so just as how then you can kind of have somewhere to ground yourself, this sort of interference occurs. This is the kind of interference that occurs that allows you to see rainbows on like the shimmering rainbows on like the surface of an oil slick, right? That's why it looks so colorful. It's because of this type of interference. So just to back up, typically, at least up until now, interference sources are separated side by side, like in the double slit case. By the way, that laser that I showed you is a very special laser. It's not one that you can buy from the store. It has a wavelength of 671 nanometers exactly, and it has a really good beam quality. That's why it looks like it's in such a fancy case. Anyway, so they're typically separated side by side. So you'd have like one beam source and another beam source, and then they interfere because they travel different distances. But what if they were separated along the direction of motion, the beam sources? Now you might think, well, that doesn't make a whole lot of sense. How would you do that? Turns out that it's actually relatively easy. So if they're separated along the direction of motion, that would mean that you have like one source that's going this way and then the same source or the same phase that's going in the same direction. You might think that that's confusing, but it turns out that the way that we do this is by reflections off of two surfaces. If light reflects off of two surfaces, then it'll reflect off of both of those surface interfaces. It'll reflect off of one and then another, and then they'll bounce back and interfere with each other. I'm going to draw a picture here. And unfortunately, I'm actually going to have to show you GIFs from the textbook because I just can't draw I just can't do animations live. So the picture is you have a light wave coming in. It reflects off the surface. And by the way, we're imagining that these light waves are actually perpendicular to the surface, but I'm just drawing them at an angle so that you can see them separating. So some of the light wave is going to reflect off the surface. We learned about this. Waves reflect off of changes in medium. And so if your medium goes from air to glass, the speed is going to change between air and glass. And so there will be a reflection and a transmission. And then some of the light wave will also pass through and reflect off of this next medium because there's an interface there. And then these two waves, so this comes in this way, and then one wave reflects here, one wave reflects here. Shoot, that pen's gonna break eventually. I'm gonna feel really bad because it's not my pen. So these two, come on. These two waves have traveled different distances. And we're imagining that this is just a way to visualize them being stacked on top of each other. They actually are aligned with each other. If this had come in parallel or perpendicular, then one reflected wave would look like this, and then the transmitted wave would keep going through, and then another reflected wave would look like this. So they would interfere with each other. It's just harder to visualize that way, so that's why I put them at an angle, so they separate. But imagine that these are indeed overlapping, and they are traveling in the same direction and so on. Like this is just an abstraction that we have to use to visualize these things. But they've traveled different distances is the important part. One has traveled all the way through the medium and back again, and the other one reflected off of the first interface. So the way that we can create this phenomenon where you have interference as a result of two waves being separated in space by or along the direction of motion is by creating a thin film reflection, or reflection off of a thin film. The light comes in and reflects off the first interface, and then the part that continues on through also reflects off of the second interface. And then they're separated by distance. They've traveled different distances, but they're still from the same source of light, which means that they're still coherent with one another. They're still in the same phase, they're still the same wavelength, and so on and so forth. So before we can continue, we need to talk about how the speed changes in different media for light. So let's talk about light in a medium. So when light enters a medium, we already know that it's going to change speeds, right? This is true for strings. Like if you put a wave on a string, if the string is thick, it'll have a different speed than if the string is thin. If you change the tension, it'll change the speed. Same with sound. Sound traveling through the air, 340 meters per second. Traveling through the water, something like 1,000 meters per second. The speed changes as the medium changes. So the speed of light is medium dependent. So when people are talking about, oh, things can't travel faster than the speed of light, really what they're saying is things can't travel faster than the speed of light in a vacuum. So the speed of light in a vacuum is 3 times 10 to the 8th meters per second. The speed of light in other substances is going to be slower. In particular, you can actually send light through a Bose-Einstein condensate, a particular rubidium gas, basically. And this was done, I think, like 20 years ago. You can actually, depending on the medium that you send the light through, you can slow it down so much that you can walk faster than it. So this is a thing that can happen. You can affect the speed of light by changing the medium. Now, just to be clear, there are no media that increase the speed of light, only decrease the speed of light in that medium. So for light, the change of speed is controlled by a particular number that is a characteristic of that medium. It's controlled by the index of refraction. And that number, it's a variable, and that variable takes on different numbers, is usually labeled by the lowercase letter n. So the index of refraction for one material would be one number, and then the index of refraction for another material would be a different number. But you would say that like n1 equals 2, and n2 equals 62, or something like that. So like I already said, the fastest that light can travel is in a vacuum, it's c. It's 3 times 10 to the 8th meters per second. In a medium, the speed of light v is c divided by the index of refraction in that medium. So you can see that if the index of refraction is greater than 1, then the speed of light shrinks. And in particular, the index of refraction is 1 for a vacuum. And the index of refraction is greater than or equal to 1 for all media. Media being the plural of medium. That's just true. So the index of refraction for water is like 1.33. The index of refraction for air is like 1.004. The index of refraction for glass is like 1.5 to 1.6. The index of refraction for diamond is like 2 point something. So the point is these indices of refraction just vary. They depend on the material, and it's just something that you measure. So now I need to remind you of one more thing. The frequency of a wave, f, is determined by the driver of the wave. So it shouldn't change regardless of what's happening. The way to think about this is that, like, if I'm driving a string by like moving it up and down, the string should move up and down at precisely that rate, regardless of what medium it's in, right? Because I'm moving it up and down, and that's the rate that it's moving up and down at. So when we, yeah, f is frequency. Frequency. I'm going somewhere with this. So that means that, and the, how do I want to, oh, okay. So maybe I should have said that later. Quick reminder that the speed of a wave is related to its wavelength times its frequency. So now we can say, oh, remember that the frequency depends on what created the wave to begin with, so it shouldn't change depending on the medium. So if the wave speed changes and the frequency stays the same, f does not change when it enters a medium, that means that the wavelength must change to accommodate for that, because this equation is always true. This implies that the wavelength, lambda, changes when the medium changes. So light slows down in the atmosphere? Yeah, but just a little bit. The index of refraction is also, so the index of refraction depends on a lot of things, but one of the things it depends on is the density of the material it's traveling through. You can think of like the light, here you have to imagine it like photons. You can think of like the photons bouncing around. The more stuff there is, the more stuff it has to bounce off of, so it's not going to make as straight a path. But for air, it's not very dense. There's not a lot of material, so it travels a lot further before it bounces. That's not like an accurate picture, but that's a way to think about it. That's a way to conceptualize this notion that the speed of light slows down as it passes through a medium. And air is not dense, so it doesn't slow down very much. It slows down by like a factor of 0.4% or something like that. Right, so the wavelength changes, but the frequency stays the same. And the wavelength changes in precisely the right way so that the speed that we would measure is the speed that we get from dividing the vacuum speed of light, c, by the index of refraction. So just to put this another way, the wavelength gets shorter when the light slows down. Okay, so mathematically, we can write that f times v times lambda 1, f is just, so for, okay, let me be more precise here. So for a given wave, a given light wave, with frequency f in a medium with index of refraction n1, yeah, let me write that, with index of refraction n1. Then we can write that f times, say, lambda 1, the wavelength in that medium, should be equal to v1, and v1, we've already established, is c divided by n1. And so that implies that we can just solve for lambda. So lambda 1 is just a c divided by f times n1. Okay, so far so good. But we can also put that same medium, or put that same light wave through a different medium. F times lambda 2 should be equal to v2, which is c divided by n2, say where the medium, say, has index of refraction n2. And so we can we can solve both of these equations for c over f, i.e. lambda or n1 lambda 1 equals c over f. And in this case, lambda 2 is equal to c over f n2, which means that n2 times lambda 2 is equal to c over f. And because these are the same waves with the same frequencies, that implies that n1 times lambda 1 is equal to n2 times lambda 2, which is a useful relationship whenever you have a light beam that's changing medium. If you take the wavelength in one medium, multiply it by the index of refraction, and that will give you the wavelength in the other medium multiplied by the index of refraction in that medium. It's a good way to solve for these. It's a nice mnemonic. Okay, so this tells us how the wavelength changes, or how the light wave changes as it changes mediums in media. In particular, it changes wavelength according to this relationship. So now we can go back to thin film interference. I want to make sure that, did I skip a thing? No, I didn't yet. Okay. Okay. So as a reminder, again, and I know I say that a lot, but physics is very cumulative. Interference depends on the total phase difference, right? Whether it's constructive or destructive. Delta phi being the total phase difference. This is 2 pi delta x over lambda plus 2 pi f delta t plus delta phi. So what we're just going to do is we're just going to imagine that we set t equal to 0 for both of them the moment the light wave hits the first medium, hits the thin film, because then both the reflected wave and the transmitted wave will have started at the same time. And so we can just say that there is no time difference, that they've been on for the same amount of time. So we're just going to call that 0. Just makes things easier. And this isn't an approximation or only applies in a single case. We can just always make that choice. It's just a choice of coordinate systems, really. So now we have to consider a few different effects. So now there's 3 effects to consider of the thin film reflection. So first, the thickness of the film. So if the thickness of the film is tau, which is like a curly T, by the way, it's a Greek letter. Tau. Then one wave is going to travel further than the other. One wave travels 2 tau further than the other. The reason I'm smushing it here is because I'm going to draw a picture. So we have one wave coming in. Let's say that this is our medium, or this is our film of thickness tau. So wave comes in, one wave just reflects off, other wave passes through, and then passes through, reflects off, and then comes in. So the top wave, this one, will have traveled 2 tau less far than the bottom wave, because the bottom wave went through the film twice. And again, remember, these are entering perpendicular to the surface. I'm just drawing them at an angle so you can visualize it. So in this case, that means that delta x, the distance that one traveled further than the other, is just 2 times tau. Okay, what about the index of refraction? The index of refraction affects the wavelength. And so we actually are only interested in, so remember that this wavelength changes depending on the medium. So we are interested in how many more units of phase does one wave go further than the other wave. Now, in particular, if say if this top wave, say it traveled distance d, then the bottom wave is responsible for all of the extra delta x. It's responsible for the extra phase difference. It travels d plus 2 tau, but importantly, the extra 2 tau that it traveled was in a different medium where the wavelength is different. So because the wavelength changes in the medium or in the film, then the 2 pi delta x over lambda, this lambda refers to the wavelength in the film. Because the amount that the wave advances in its oscillation, the amount that the wave advances in its oscillation depends on the wavelength in the place where it's oscillating. So we care about how many more humps and bumps has it gone through while it's passing through this film. We don't care about the actual distance. We just use the distance as a proxy to figure out how many humps and bumps it's gone through over that new distance. But because the distance between humps is smaller it doesn't have to be smaller, is different in the medium, we have to use the wavelength in that medium to find that phase. So this should be lambda in the film. So when you're computing this, not only is delta x equal to 2 tau, lambda is a different thing than it was outside of the film. So this, for example, might be, it doesn't have to be depending on how you label it, lambda in the film might be n times lambda out of the film, divided by, well, actually, I'm not even going to write that. It just is the lambda in the film. And depending on how you were given the lambda, like say you were told that the wavelength is 500 nanometers, but it's in water, and then it enters glass, then you'd have to, then to find the 500 nanometer wavelength in the water, or to find the wavelength in the glass, you'd have to relate it to the wavelength in the water by using this relationship above. Okay, so that's the second effect. The third effect is perhaps the trickiest one to grasp, and that's that there are phase changes from reflections. So just as a reminder, when a wave reflects off of a slow medium, remember the thin string and the thick string? The reflection is inverted. And we established that an inverted wave, an inverted cosine in particular, has a phase change, or a phase difference, that's right, phase change, of pi. So whatever its old phase constant is, the new phase constant is the old phase constant plus pi. And so even if they started off with the same phase when they entered, depending on how the speed of light in these media, depending on how the speed of light in those media relate to one another, if one's greater than the other and so on, then one, possibly 0, 1, or more, or 2 of those, either 0, 1, or 2 of those reflections will have this additional phase change in the phase constant. And so you'll have to find the phi nu of both of them, and then you'll have to subtract those. Now, the end result is that you either get a phase constant or a phase constant difference of either pi if exactly one of them goes from or reflects off of an interface that goes from fast to slow, or you'll get a phase constant difference of 0, where either they both reflect off of an interface that goes from fast to slow, or they both reflect off of an interface that goes from slow to fast. So that will affect the interference, right? Because the whole point of interference is that you get constructive when the total phase difference is, say, 2 pi or 4 pi or whatever. So if this is 0, then you'll get one answer for, for when you have constructive interference or destructive interference. And if this is pi, you'll get a different answer. In particular, by the way, because these waves end up aligning themselves again after they both reflect, either you get constructive interference forever after they both leave the new medium, after they both reflect, or you get destructive interference forever, or you get somewhere in between. The point is that we only need to find the phase difference, say, at the moment that they recombine, after they both exit the film, because that they don't accumulate differences in phase after that point. They're both traveling through the same medium with the same frequency and so on. So we're only interested in the phase difference at the moment they recombine. So we can put all of this together, these three factors. We can find where the dark spots are. Or when do we get destructive interference? i.e., at what thickness and what type of medium do you get nothing reflected back? Because remember, if you shine a light at this interface, it reflects off one and then it reflects off the back interface as well. If you have destructive interference reflected back, that means that no light comes back. They're destructively interfering. You don't see anything. Whereas if you had constructive interference destructive interference reflected back, constructive interference reflected back, then you would see light. So the question is at what thickness of the film and at what how many inversions, how many wavefront inversions, and so on, what situations do you get destructive interference? That's what we're trying to answer. So to get destructive interference, we need that delta phi, the total phase difference, is equal to an odd integer multiple of pi. So this would be pi, 2 pi, 3 pi, pi, 3 pi, 5 pi, and so on. And so if that's true, that means that we need that 2 pi delta x over lambda in the film plus delta phi is equal to 2n plus 1 times pi, where n is just some integer again. -2, -1, 0, 1, 2, ... Right? And remember here, not recall, it was 2 minutes ago. Delta x is 2 tau, and delta phi, little phi, is equal to pi if there's exactly one reversion. Sorry, if there's exactly one inversion, meaning that one of them gets that extra phase change, but the other one doesn't. And the difference in phase constants is 0 if there are 0 or 2 inversions. If they both invert, then they both get this extra phase of pi added, so the phase difference is still 0. And if neither of them invert, then the phase difference is also still 0. So slapping these together, putting these together again, combining all these factors, we get that for one inversion, we get destructive interference when 2 tau, and now I'm just solving this, by the way, when 2 tau is equal to m, oh, I should be using m there, not n, because n is used for index of refraction, sorry, 2m. There we go. So when 2 tau, 2 times the thickness, is equal to m times the wavelength in the film, we get destructive interference. And for 0 or 2 inversions, our formula for destructive interference occurs when 2 tau is equal to m minus 1/2 times lambda in the film. So there's 2 separate cases, and the reason there's 2 separate cases is because the phase constant difference affects, and hence the number of inversions affects the outcome. So this is again, m is equal to minus to dot dot dot. It's just equal to integers. -2, -1, 0, 1, 2, dot dot dot. Any possible m. So this, yeah, so this gives us a something that we can calculate. Now the question then is like, why do we care about this? Well, actually, I think I'm going to do an example for you in a minute, but I want to walk you through a visualization of what's happening, because I know that this is hard to visualize. So I'm going to share screen to the diagram in the LibreText, which is an excellent diagram, by the way. So go back and look at it if you want to spend more time on it. So here we're going to look at this this diagram here. So let me put this up here, sorry. So imagine for a moment that we have a wave going towards an interface. Now here we have 3 different media. We have, say, air maybe on top. This would be N1, whatever that index of refraction is. Then there's a really thin layer of width tau that has index of refraction N2. Maybe it's oil, maybe it's glass, maybe it's water, whatever. And then below that is another layer of, or is another medium with index of refraction n3. We're not going to worry about what's below n3 because we're just interested in the first reflection, the reflection off of this surface. We're also going to assume that n2 is greater than n1 and that n3 is greater than n2. What does that mean? Well, that means that n2, that the medium n2 is slower than the medium n1, and the medium n3 is slower still. Also note that we've that the solid lines are the peaks here, and the dotted lines are the troughs. And so if you were to take a measuring tape, you'd find that this is, I think it's what, two periods. The thickness is exactly 2 wavelengths. Let me just double check. Yeah, so look at the distance here. So that's 2 wavelengths, and this thickness also happens to be 2 wavelengths. Oh, why does it say it's 3? Is that actually 3? Okay, well, we're going to assume it's 3. No, sorry. Let me be clear. It's 3 wavelengths inside the medium. So because n2 is slower than n1, the wavelength is going to decrease. So while it looks like it's something like 2 outside of the medium, once it gets in the medium, that wavelength is going to shrink, and then you'll be able to fit 3 wavelengths in there. This is just something to make the visualization easier, but this doesn't have to be the case. Right, so the wave comes in, enters the first medium. Now there's going to be a reflection and a transmission. Now we can look at both of these. So the reflection, you might say, well, wait a minute, when something reflects when something reflects, the leading edge should be the first part that's reflected. So the first part that hits the interface is a peak. But because the medium that it's reflecting off of is slower, it has a higher index of refraction, that means that that there would be an inversion upon this reflection. So here we see that the leading edge of the reflection is a dotted line, meaning that it is a trough. So the wavefront was inverted. It went from a peak, the leading edge was a peak. Now the leading edge is a trough, and that's because of this inversion. Okay, so this is just going to keep propagating upwards, and eventually the transmission will reflect again and then recombine with the first. So the wave that was transmitted, that never inverts. It just always is what it is. In this case, again, the leading edge is a peak, but note that the peak and trough are closer together, and that's because the wavelength is shorter here because it's a slower medium. Okay, so this is after 1 period. After 3 periods, the reflected wave is reflecting 3 periods up. Notice that the leading edge is still a trough. And here we have in the medium, we have that exactly 3 periods fit in this film. So we have that the peak has moved all the way down to the bottom. That's exactly 3 wavelengths. Now it's going to reflect again off of the second interface, the bottom interface. So that wave is going to reflect, and there will be another inversion. And the reason there's another inversion is because n3, medium 3, is even slower than n2 because it has a higher index of refraction. So we get another inversion. The original wave had was leading with a peak. The reflected wave is leading with a trough. So we have 2 inversions here. So this would be applying in the 2 inversion case. Now we just wait another few periods. In this case, we'd have to wait 3 periods. So that was 4 periods because there's 1 more after it was reflected. Waiting another 3 periods would indicate that now the peak, or sorry, the leading trough of the secondary reflected wave is just about to leave at the exact same time that a trough would be reflected from the first interface. So now we can see, and by the way, the wavelength just goes back to what it was after it leaves the interface. So now we have this trough is emitted. This is exactly 1 period afterwards. So this trough would have gone up 1 period, 1 wavelength. But now we see that that is precisely adding up with where would be a trough from the red reflected wave. So the blue reflected wave and the red reflected wave are both having troughs at this location. Similarly, they'll both have peaks at this location. And so what we have as a result of this is constructive interference from this reflection. So we can look at the total phase changes and compare them. I'm going to zoom in and show you. So the first reflected wave, it gets an inversion. So the accumulated wave, or the total phase difference between the incident wave on the surface and the reflected wave differs by just pi, because the wave goes from not being inverted to being inverted. For the second wave, it starts off with the incoming phase, and then it travels a distance. Now it travels a distance equal to 6 times tau. Sorry, 6 times travels a distance equal to 6 total wavelengths, right? In this case, and then we multiply that by 2 pi to get the total phase change. And there's a reflection off of the bottom. So we have an extra factor of pi because, sorry, not reflection. There's an extra inversion at the bottom down here when it reflected here. There's an inversion, so we get a pi there. So then we just need to figure out what this is. But we already established that there are 6 wavelengths in the distance that it traveled. So delta x over lambda should just be 6. So we can plug that in. We get 2 pi times 6 lambda over lambda plus phi incoming plus pi. So this is phi incoming plus 13 times pi. It's phi incoming plus 2 times 6 times pi plus pi is 13 pi. And so the total phase difference between these two reflected waves would be 13 pi plus phi incoming minus pi plus phi incoming. Now the phi incomings are going to cancel out as we would expect. And all we're looking at is how the phase changed because of the different phenomena encountered, because of the reflection, because of the extra distance it traveled, and so on. So we get 13 pi minus pi is 12 pi. That's an even multiple of 2 pi, or that's an even multiple of pi. It's 2 pi, 4 pi, 6 pi, 8 pi, 10, 12. So we get constructive interference. So off of this interface, sorry, off of this film, where the film's thickness is 3 wavelengths, where the wavelength is measured inside the film, that would create constructive interference. This is just a single example. You could do this for where N1 is slower, or N1 is less than N2, but N3 is also less than N2. You could do the same thing. You'd get destructive interference and so on. You could just do this for a whole bunch of different scenarios. Now, what I'm going to do is I'm going to do an example for you, just because I know I've thrown a lot at you. So I'm going to do an example so you can see how this works out. So it's going to be a simple example, so you have to bear with me. It's just going to be glass. It's going to be vacuum, glass, and then vacuum again. So this is like a window if it were surrounded by vacuum. Oops, participants and chat. Okay, so we have glass and then we have vacuum. So the index of refraction of glass is about 4/3. The index of refraction of the vacuum is exactly 1. Oh, sorry, we'll use air rather than vacuum, but air and vacuum basically have the same index of refraction. So let's just use air. So this is like the kind of interference that you would get reflecting off of a window, right? You have air inside your house, window, air outside your house. This is exactly what we would expect. So draw a quick picture. You have your glass window pane. By the way, windows don't actually work for this because like the glass in window is way too thick. But in principle, you could make a really, really thin window and then you would see this sort of effect. So delta x in this case, let's say that this distance is d, the thickness of our window. So delta x in this case is 2 times d, because the reflected wave, and we have light coming in this way, then it bounces off, and interferes back with itself, right? So that's what we're going to work with. So the distance that the secondary reflection traveled further is 2d. Now, what about delta phi? How far, or where are the inversions? Well, we know that when the light goes from air to glass, the index of refraction goes up, which means that the speed through the glass is slower, and so you get an inversion. So we get an inversion here. Now, so the first reflection will have an inversion. What about the second reflection? So it just passes through the glass. You get no inversion from passing through the glass, and then it reflects off of the glass-air interface. Now there, you're going from a slow medium to a fast medium, so you get no inversion off of this back edge. So the total phase difference as a result of the inversions is pi, because there's exactly 1 inversion. one of the first wave gets a pi, the second wave gets 0, and so delta phi is pi minus 0. It's pi. So what about the index of, or what about the wavelength in the air? Well, this would just be the wavelength, sorry, the wavelength in the glass. Wavelength in the glass is the wavelength in the air divided by 4/3, which is the index of refraction of the glass. We're assuming that the index of refraction in the air is 1. Otherwise, you would need an air up here. But we're assuming it's 1, so we cannot have it. So this should be equal to just 3 lambda air over 4. So now we can find what the total phase difference is. So delta phi is 2 pi times delta x, which is 2d, divided by the wavelength in the glass. Ugh, I can't talk today, which is 3 lambda in the air divided by 4 plus pi. This is delta phi. So this works out to be 16 pi d over 3 lambda air plus pi. So this is what the total phase difference would be, which is to say, if lambda air and d conspire to make delta capital phi, the total phase difference, pi or 3 pi or 5 pi, etc. Like if they are, like, you can just choose d and lambda air, like maybe you'd use a different color light or maybe you use a different thickness glass. If they conspire to make that be the case, then you would get no reflection, because any reflection would destructively interfere from both ends. And so you might wonder, okay, why do we actually care? And that's always a good question to ask in physics. I promise it's a good question, and I promise there are good answers to this. By the way, before I continue, there are good examples that I wrote in the lecture notes that you'll be able to take a look to get your practice later. Right, so you might ask why you care. Well, one reason why you might care is that this is a really good way to make perfectly transmitting mirrors or perfectly transmitting glass. If you've ever looked at like a window and shown a flashlight out a window, you'll notice that there's a reflection, right? And like quite a bit of light is lost off of the reflection, something like 4% or so on average from white light is reflected off of the window. So if you wanted to make a window that was perfectly clear to like a laser, for example, might be useful, a non-reflective window. Well, you might want to do this, for example, if say your laser is in like some like it is in a vacuum and you want to make sure that all of it goes through. Then what you can do is you can apply a thin film to the window that makes it makes that chosen wavelength precisely destructively interfere, which would be very, very good, because then you get full transmission. If the wavelength if there's no light that's reflected, then all of it has to be transmitted by energy conservation. So you would let all of your light through. Other ways that you can use this are basically ways to reduce glare. So why do we use lambda air? Is lambda air in the film? No. Lambda glass is the wavelength in the glass. The film in this case is just glass. And so you can use this to, like, by just applying a really thin film of like plastic or whatever, you can change the reflective and the transmissive properties of whatever material you're interested in. That buys you a lot. You can make really high quality optical devices by applying films. Like if you've ever had a well, okay, no, that's a slightly different phenomenon, but which we will also talk about. This also explains, by the way, why an oil slick on, say, the ocean swirls, because as the thickness in the oil changes ever so slightly, the reflected wavelengths the reflected wavelengths that destructively interfere change with thickness. So in some places you might get wavelengths that destructively interfere that are red, and so it looks bluish green. In other places you might have destructive interference that is blue, and so you would look reddish green, and so on. So you can get different colors reflected in different places. And in fact, the thickness of the film exactly tracks with the wavelength that's reflected. So the lines and the swirls that you see in an oil slick, those basically map out like a topographical map of the thickness of the oil on a scale that we can visualize. Like these things are micrometers or even smaller thick. And so the fact that we can see these lines on the oil indicate that the height, the thickness of the oil is slightly changing at different places. So this whole phenomenon of thin film interference, super useful and super interesting. I'm going to end lecture there. I promise I'm not going to stop the lecture. I'm just going to stop the recording.